usually eliminate two things from a substrate. So you're going to eliminate usually HX or some leaving group. So you're going to remove two things and you're going to form a double bond. So double bond formation is the hallmark of basically anything with an elimination reaction. So because of this, then we need to figure out what double bond are we going to form. And so what we do with this is we follow what's called Zachev's rule. So Zachev's rule there we go, Zachev's rule. And so what this means is that we're going to first form the most stable double bond. So we're going to form the double bond that is the more substituted double bond. So the higher substituted alkene is what will be formed. So the more substituted alkene is formed. And as an example of this, you might have something that looks, for instance, like this, where we have a leaving group here. So I'm going to represent that with just Lg. And so what you can see is that you're going to notice that we have hydrogens that are here. There's 3 of them here. And we also have a hydrogen that is here. And so we can eliminate this using a strong base. So I'll just represent that with B-. And we can eliminate the hydrogen that is here, which means these electrons go in there, and then these would kick out to the leaving group. Or we can eliminate the next possibility, which would be this one, which would force these into there and also kicking out your leaving group. And so you can see that you would end up with 2 products here in this case. So one would end up with a double bond right here, and you would then also end up with one that would have the double bond that's right here. This one is the more highly substituted double bond, meaning that we have one R group, a CH3 here, and one R group here. This one on the other side, we have only 2 hydrogens that are coming off of this double bond as substituents, so therefore, and one R group here. So therefore, this double bond is less substituted. In other words, less substituted by R groups. So what that means is that this, according to Zachev's rule, this is the more highly substituted double bond, and so this would be our major product. That doesn't mean that you will only get this product. You will get some of the other, but this one would be in lesser amounts. So this would be the minor product. So when determining what's going to happen with elimination reactions, you have to consider the overall stability of the double bond. So you're going to use Zachev's rule to determine the overall stability of the double bond. Now, with that being said, there are 2 major types of elimination reactions that we are going to discuss. And we have what we refer to, just as we had 2 types of substitution reactions, we have E1 reactions and we have E2 reactions. And just like with substitution reactions, E2 reactions are concerted and happen in essentially one step. Therefore, it's what we call a bimolecular reaction. In other words, the rate of this is determining is important essentially on both parties, Rx or R in your leaving group, plus the nucleophile or base that you're going to use. So we don't have any intermediates. So E2 reactions are bimolecular, and so we end up with essentially both species for the rate. So if we have something, our rate for this would be, just like with substitution reactions, it would be K times, and I'm just going to note Rx, or it could just be R in leaving group, whatever that may be, times the concentration of your base. SN2 reactions, E2 reactions, of course, are bimolecular, and so what that means is they occur essentially as a concerted step, and so we can look at this and envision as something that may show up like this, whereas you have some R group here and another R group, and then we have our leaving group, which I'm just going to denote with S or X, and we have this hydrogen that's here plus some other R group. It doesn't really matter at this point what the R groups are, right? And so what we're going to see happen is we're going to treat this with some base that I'm going to denote here with B minus, and the base is going to pick up this hydrogen. The electrons are going to move to between these two carbons here, kicking out your leaving group, which would be in this case X minus. And so what you can see is that this happens all in one single step. Now we have our double bond, and we have our R groups that are out there. But one of the things that you should note is if you were to look at this and draw this in a sawhorse type configuration, what you can see is that here you have your R groups, hydrogen, X, and our other two R groups that are right here. Notice how this one, the hydrogen is up and your X or leaving group here is down. So what you can do is convert this into a Newman projection, so that would look something like this. Where you have this as X, this is H, and then of course the rest over here are your R groups. And so notice how we have this type of configuration where we have what we call this anti-periplanar geometry. So this, for E2 reactions, we must have this anti-periplanar geometry. So we need this anti-periplanar geometry. Basically, all of the reacting atoms are going to lie in the same plane. They're just going to be opposite of each other. So if we have a plane that goes up and down here, notice that in this plane that is going up and down, we have the hydrogen and the X are all in the same plane. They're just opposite of each other, and that gives us this anti-periplanar geometry. So what this means is then all of the reacting species are in the same plane. Right, so we end up with this anti-periplanar geometry. This is what's important for E2 reactions, type of geometry. E1 reactions now, so E1 reactions, and whereas with SN2 reactions or E2 reactions we wanted strong bases, in this case we're going to want something that is a weak base. And the other hallmark that you can look out for is that we want a substrate that would be similar to SN1 substrates. So we need same substrates as SN1. Right. So what that means is that we want a substrate that can stabilize a carbocation. So forms the more stable carbocation. Okay, so as an example of this, you might think of something like this, where we have, say, T-butyl bromide, and we're going to react this with some water and some methanol. The methanol just being there to help solvate everything. So we'll just say water and a little bit of methanol. Mostly we'll have water in solution. And so we can do this at, say, 70 degrees. And what you'll see is you end up with two products. You end up with this from your SN1 product, and then you end up with your eliminated product from your E1 reaction. So E1 reactions give you the are always compatible in some sense with SN1 reactions. So let's look at the mechanism as what's happening here. So mechanistically, you already know that you're going to go through a similar pathway as with SN1 reactions. So that means that you're going to form your leaving group, or have your leaving group leave, and so this would then be the slow step, right, or the rate determining step here, which we abbreviate with RDS. So this is your rate determining step, and what's going to happen is, of course, these electrons are going to leave and go to your leaving group, and now you end up with a carbocation. And for the elimination reaction to take place, notice that we have to have this hydrogen that's going to be here. And so we are going to see that we also have a bit of water in solution. And we're going to go ahead and form the double bond now. Once we have our stabilized carbocation, these go in there. And there's your double bond. And this then, of course, is going to be what we consider the fast step, right? Once you form the carbocation, the reaction is off to the races. You're going to form the next step very, very quickly. And in this case, what you notice is that we have this plus H3O plus and Br minus here. So we get a little bit more acidic as we continue to move forward in this reaction. So this is what happens with an SN or E1 reaction, which is very closely or a close analog of the SN1, and the fact that we have two similar reactions that are, or two reactions that are competing here during the process. So as you can see from this, right, that this is our slow step. So the rate of our reaction only depends on this initial step. So this happening to form the carbocation is our rate determining step. And so therefore this gives us our rate for an E1 reaction as rate is equal to K times only Rx, just like in SN1 reactions. Right. So again, we also here are forming a double bond, so we want to form the more stable double bond. So also, as another point, the more stable double bond will form, and that means that we follow Zachev's rule. Is going to be followed here. So that means we form the more highly substituted double bond. So the higher substituted double bond. Or alkene is formed here. Right, so we're going to follow Zachev's rule in this case. So that is essentially the end of the elimination reactions. Now what you should consider is that things that favor SN2 reactions also favor E2 reactions. You need a stronger base or a nucleophile for those. For E2, just like for E2, you need the stronger base, or i.e. stronger nucleophile. Remember, nucleophilicity roughly follows basicity. Right, so, and then just as another comparison, the reactions that where E1 would predominate, so does SN1. So the same conditions. So weaker nucleophiles, right? Typically the nucleophiles for SN1 and E1 will be your solvent, as was the case up here, right? That your solvent is going to be your nucleophile or your base. So make sure that you kind of get those together in your head.